So sorry for being extremely late. Hopefully I'll manage my time better for next lecture. Okay, today inshallah we'll start on discussing the basic stuff. So, but they are nice to learn some concepts, even though you might have been, some of you at least might have been through them before, but we'll try to also use them to learn some important concepts that we'll use later on in this numeric methods course. So we'll discuss today the system of linear equations. System of linear equations. Okay. And before going into exploring some numerical methods that are used on in solving a system of linear equations, we'll start first about reminding you of something important. So there are three cases for a system of linear equations in terms of whether you can find a solution or not, right? So the cases of a system of linear equations. Okay, so what are these cases? Does anyone remember? What are the three possibilities? Let's first look, okay. A system of linear equations can be written in the very classical high school approach or before high school as equation number one, which, for example, say we have n variables, call them x1, x2, up to xn. So equation number one says a11 x1 plus a12 x2 plus and so on up until a1n xn equals b1, and then a21 x1 plus a22 x2 and so on equals b2, and then you continue until you reach an1 x1 plus an2 x2 blah 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 equals bn, right? And your unknowns are x1, x2 up to xn, okay? And now this is how you write them, but then we later on came up with the matrix representation for this. So it says a x equals b, and a is, let's assume generally speaking, an n times m matrix, okay? And x has to be what? It's a vector, so it has to be a vector of what dimension? Yes, n times 1, and b has to be a vector of which dimension? Huh? No, still, yeah, m times 1, right? Okay.
Then A should be m times n, right?
So n
M times
is the number of rows, yes. So it should be the other way around. M. How do you clean here? Yes. So this should be m times n. You're right. Okay. That's correct. Okay. So that's how the general set of linear equations is represented in the matrix case. So what are the three possibilities that you have here? They all have to do with this matrix, which means the number of equations versus the number of unknowns, right? So what are the three possibilities? So you either have m equals n. This is the exact system. So you have number of equations which is equal to the number of variables, or you have m greater than n. This means what? This means the number of equations is greater than the number of variables, or you have m less than n, which means that the number of equations is less than the number of variables, right? Now there is a trick to this. It's not just simply the m and the n. We will see why in a couple of minutes. But the important thing is that we call this one the exact system, right? This is a system where you should have a unique solution. So there is only one set of values that can be assigned to the x1 up to the xn, right? The other case where the number of equations is greater than the number of variables is called the overdetermined systems. And in the general case, there is no solution here, because you have more requirements than the number of variables, and it becomes, in the general sense, it becomes impossible for you to find a set of values to the variables that satisfies all the requirements, right? Okay. And in the last one, in the general sense as well, this is the underdetermined. Yeah. And in this case, you have infinitely many solutions, right? Infinite solutions. You can just simply pick some values for some variables and then apply the equations and you get the remaining ones. And then when you change the values of those variables and you apply the equations again, you get another set of solutions and so on, okay? That's in the general sense. Now there are more constraints or more requirements or more exceptions or variations to this. The more general approach is going to be depending on the properties of the matrix A, right? So if the matrix A is a non-singular matrix, which means that you can get its inverse, then in that case you are really in this situation, right? Now, if the matrix A is a singular matrix, what happens? Means that you cannot get its inverse. And this means what? No solution or infinitely many solutions? Which one? So if A is a square matrix, let me put more specific situation. So A is a square matrix, which means that M is equal to N, right? But when you try to get its inverse, you cannot. You are faced with divide by 0 and you cannot get the inverse. So what's going to be the case in that case? No solution or infinitely many solutions? Basic linear algebra. There are two cases actually, okay? There is one case which is no solution, and we call that the inconsistent situation. I'll give you an example of that inconsistency. And there is another case which is the consistent but singular. In that case, it's infinitely many solutions, okay? The difference between those two cases is, in both cases, you have some equations that are linearly dependent on each other. So the coefficients of the x's, like that equation can be derived from the other equations, right? Except in the inconsistent case, because everything lines up in terms of the coefficients, they can be derived from the other ones, but the right-hand side, the constant, is inconsistent. Let me give you an example. If you have those two equations, right? 2x plus 1 equals 3, and another equation that says 2x plus 1 equals 5, right? Now, if you look at the matrix, the coefficients of the matrix here are going to be 2, 1, 2, 1, right? And those coefficients, if you try to take the inverse of the matrix, because the second line is exactly the same as the first line, if you try to get the inverse, you will not be able to get the inverse. So that's a singular matrix. But because of the right-hand side, right, you need to look at the right-hand side in that case. And because of the right-hand side, the problem here is not that you have infinitely many solutions. You cannot have a solution within the domain of real or even imaginary functions, or imaginary, groups or sets, right? That allows you to satisfy both equations. You can't. You can't just have 2x plus 1 equals 3 and 2x plus 1 equals 5 at the same time, okay? So that's called an inconsistent situation. If you want to look at things geometrically, and geometrically it's much easier to figure it out, okay? Now this, as opposed to this equation, for example, another example, which is singular and infinitely many solutions. So you have 2x plus 1 equals 3, and the other equation is 4x plus 2 equals 6, right? Now those two, when you get the matrix, again the matrix is going to be singular. You cannot invert the matrix, but the result of that here, or the consequence of that, is that you can put, because those two equations are exactly the same. Okay, so you can put any values to x and it will satisfy those two equations. Okay, yeah, I mean here it's just, sorry, I just need to like say x1 and x2, right? So 2x2, and here, because if it's a single variable, it's solvable from one equation, right? So x2 and x2. Okay. So these two cases will have a singular matrix, but this is an inconsistent case, and this is an infinitely many solutions case. Now, geometrically, this case is the case of a line. I'll draw it with the same. And itself, right? A line, and the second one is a line just on top of that one. While this case is the case of two parallel lines. They will never meet. A solution means you can find something that belongs to both of them. There has to be some intersection between them, right? And those two parallel lines will never meet, so there is no solution to that case, okay? So that's the case of the singularity. Now, when the dimensions change, it becomes a non-square matrix. And in the case of a non-square matrix, you cannot really get an inverse. However, and I don't know if you have been exposed to that or not, but in the two other cases, so M is greater than N and M is less than N. This is the overdetermined. Okay, and this is the underdetermined. It has been agreed that there is one solution to the second case. The underdetermined, as we said, generally speaking, will have infinitely many solutions. Again, we are here assuming a very important thing, that the matrix A in both cases here is full rank. So even though the matrix has two different dimensions, the rows and the columns, right? But the smaller one of those cannot be further reduced. So that's called a full rank matrix, right? Which means that I cannot find, in the first case, the M represents the number of, we agreed that the M is the number of rows, right? Okay, so the number of rows is greater than the number of columns. This means that when you look at the columns, you cannot find two columns that are linearly dependent on each other, or you cannot deduce one column from all the other columns, right? If that's the case, this is called a full rank matrix, right? You can no longer reduce the rank of the matrix beyond or less than the value of, or the number of columns in that matrix. And in the other case, it's an underdetermined case, which means that the smaller value is the number of rows. And if you look at the different rows, you will find that the rank of the matrix is exactly M. You cannot really, it's not smaller than M, which means that you cannot find any row which is a linear combination of the other rows, okay? So assuming that it is a full rank matrix in both cases, okay, now we can say that the first case is the case where you will have no solution, and the second case is the case where you have infinitely many solutions, right? A number of equations less than the number of variables. Now in this case, people have agreed into a solution that has a specific property to it, which is called the least norm solution. The least norm solution is a solution that gives you, if you imagine that the rows of the matrix represents a certain space, right? So the rows of the matrix, the M rows of the matrix, they span a certain space with M dimensional space. And then you are taking the projection of your overall system, which lies in N dimensional because you have N variables, right? And you project that into the M, the smaller one. What's the meaning of a projection? That you are trying to take that and represents the normal drop of that into the other one. When you have a line and you have another line here, let's talk about two dimensions, and you have another line here, the projection of this one on this one is defined by taking the perpendicular, and then this length, that comes from the point of intersection until the perpendicular and until the cut of the perpendicular, we call this the projection of this line on this one, right? So similarly here, but it's in n dimensions or m dimensions, so it's more dimensions. You are trying to project the n-dimensional space, which is the space of the number of variables, because you have n number of variables, right, into the m-dimensional space. So the projection. So it's not just taking this and just put it somewhere in the other space. You are looking at the projection point. That's the shortest point from the original solution, okay? When you try to do that, you get something called the least norm solution, okay? And this least norm solution is just one of those infinitely many solutions that you can get, okay? Now, how do you do that numerically in MATLAB? You use something called the P-inv. There is something called the pseudo-inverse of the matrix A, right? The pseudo-inverse of a matrix is composed, it represents this projection operation, and it is composed by multiplying the matrix by its self-transpose. So you take A, and you multiply it by A transpose, and then you take the inverse of that. Now, if A is a full rank matrix, it's guaranteed and from linear algebra rules, and you don't have to prove that or anything. If A is a full rank matrix, then A transpose is definitely non-singular, okay? So it will be a non-singular, and at the same time, it's going to be a square matrix, so you can take its inverse. It's guaranteed that you can get an inverse for that, okay? And in this case, that inverse, you can use it to solve for x, the variables, right? But you cannot get all the x's. You can just reduce the set of variables into m variables only, right? And you can get a solution for those m variables, and that's called the least. If you get that solution using this representation, this is going to be multiplied by b, of course, right? Because in the general sense, when we have ax equals b, the solution, if there is a solution, is going to be a minus 1b, right? So here, instead of doing this, we have the a transpose, right? And then we take that to the other side. And of course, to keep the equation as is, so you have ax, right, equals b. Now, in order to get the a transpose, right, we multiply this side by, a transpose minus 1, a transpose, and we multiply the other way. We multiply the a transpose here, okay? And this means that you have here the a transpose as well. So multiply from, the dimensions are correct in this case, right? B is m times 1, right? And then A transpose, sorry? Yeah. Yes, so now this, yes. And then I have to change this one. So this one becomes A transpose A to the power minus 1. Yeah, so if we do that the right way, so it's A transpose A, and then this one also becomes A transpose here times B, right? And then you multiply by the inverse of this from both sides. So A transpose A minus 1, and also here I got stuck. A transpose A times minus 1. So the solution becomes actually A transpose A minus 1 multiplied by A transpose, right? X is equal to this. That's the solution that you get in this underdetermined case, and it's called the least norm solution. And as I mentioned, in terms of geometric representation, it's just a projection on the smaller space represented by the number of rows in that case, okay? On the other case, the case of overdetermined situation. Now you have m greater than n, which means that the number of equations is greater than the number of variables. And in that case, we get another solution, also using something very similar, but the pseudo inverse is the other way around. We'll see how. But the solution that we get in that case, in terms of the meaning, you can think of it, they call it the least square solution. And you can think of it as, imagine that those equations that you have were representing samples that you take from a certain process, right? And then remember curve fitting, and you are trying to figure out the curve that fits those samples, right? In this case, we are trying to figure out kind of a linear solution to those samples, right? How do we do that? We typically represent that by the line that has the smallest sum of the square errors, right? Or another approach was using the absolute difference in the y direction, for example, and we select the line that has the smallest sum of the absolute y errors, right? That's kind of doing a fitting. And then in this case, you cannot find something that satisfies all the equations, but you try to find the trajectory which is minimizing the difference from the set of equations that you have. So the set of equations is ax equals b. Then you say that I cannot find something that allows me to get ax minus b equals 0. This is not possible. Okay? So I would say that I will try to find, generally speaking, what I can get is that ax minus b equals some error value, right? It's going to be some value which is not equal to 0. And then I find the solution for this. I find the e, which is minimal. And to minimize this e, this is going to allow me to find one single solution for the x variables. Okay? So that's basically how they do that. It's called the least square solution. And again, that one is using a pseudo-inverse approach, but the pseudo-inverse becomes the other way around. So it becomes A transpose A transpose minus 1 multiplied by B and the x from the other side. So this is for the overdetermined case. And this is for the underdetermined case. Okay? In both cases, you are using a pseudo-inverse approach. You cannot really do an actual inversion of the matrix because the matrix itself is non-square. So you cannot invert that one, okay? And this, both of them, you use the same MATLAB command, pmv, pseudo-inverse, and the MATLAB performs the operation correctly, knowing what's the m and what's the n. So basically, knowing if the m is less than n, then it uses the second one, and if the m is greater than n, it uses the first one internally in the operation pmv itself, okay? That's just a quick reminder. Any questions about this? Just a quick reminder about linear equations, different cases. And of course, if you want to solve the exact case, then you have the command in MATLAB, which is called env, right, of A. This one allows you to get the inverse directly, the inverse of A, and then using the fact that x, the solution, is equal to the inverse of A multiplied by the vector B, you're going to get exactly the final solution. Similarly here, by the way, this is the pmv. So the pmv is not the full solution. The pmv is just this part of the equation, and then you can take that and either multiply it by A transpose from the left and then B from the right to get the overdetermined solution case, or you multiply it by A transpose from the right and then B from the right to get the solution for the underdetermined case, okay? Now, the command itself is not really, especially the inverse command in MATLAB, is not really doing the inverse using the classical operation, okay? It's using itself, the command is using a numeric approach to get the inverse of a matrix. Why this is the case, and that's why I just said that today we are going to touch upon some. So if you look at any numeric solution approach, okay, that's a conceptual thing. in any numeric solution approach, you are trying, as we said last time, number one, to increase the accuracy. So you want to make sure that you are getting a solution which is very close to the exact solution, right? Number two, you are trying also to make sure that it's converging. Converging. Okay, it's a conversion. Conversion is not a course, it's not a ensure convergence. Easier to write it this way because it's not a verb. So ensure convergence. Okay. Not conversion, conversion. Convergence. This is the correct word. Okay. So you're trying to ensure convergence, that it is approaching the solution. It doesn't just go away from the solution. And then the third, and it's very important, what do you think is the third important thing that you need to look at? Error, maybe anything related to the error, you will put it here for the accuracy. And the convergence is just to make sure that it's correct. It will get you a correct answer, right? It's not just that it will have some small errors. It will actually get you something correct. It will not go away from what you want to achieve. So what's the third thing that you care about in numeric solutions?
Number of solutions. Speed.
Yeah. So maybe you meant number of operations, I think, yeah, right? So the number of operations or the speed. So getting to the solution in a quick way. It doesn't take forever until you get to the solution, right? So speed, or you calculate that using number of, to be fair, I mean, calculating speed using time is not, at the time it takes to get the solution is not fair, because typically you're using computing platform, and it relies whether you are using a fast computing platform or a smaller one. So typically they do that by the number of operations. How many operations I perform, particularly they consider an addition, a subtraction, a multiplication, a division, a logic. All of these, they consider them as one-step operation, because typically in nowadays hardware, they are performed in one step on the hardware, okay? So the number of basic operations that you have to perform in order to get to the solution. Now the idea for the env is that if you perform the inverse of a matrix using the classical approach, which is go and calculate the determinant of the matrix, and then after calculating the determinant of the matrix, you start doing those replacements of each element is replaced by its corresponding determinant, right? So imagine how many determinant you have to calculate. I know that they are reducing in dimension, but you still need to calculate a large number of determinants, and determinants are typically very time consuming because you have many multiplications and subtractions or additions, right? So the calculation of determinants, and then let alone that you are not only calculating one, you are calculating many of them depending on the number of rows and columns, right? Becomes a very expensive operation. And there are numeric approaches, we will touch upon them next time, inshallah. There are numeric approaches that you can use to calculate the inverse of a matrix, okay? So typically this operation, and even the pseudo inverse, is not calculated by doing matrix multiplications and then inverting. There are also algorithms that allows you to calculate the inverse and the pseudo inverse numerically, right? Rather than using the exact operations, okay? And those ones are typically much faster. That's the whole idea. They do suffer from not being exactly accurate. They have small error to them, right? Of course, they have to be converging. Otherwise, the whole thing is not, it's an incorrect solution. But it's typically sacrificing small error or less accuracy to gain a lot of speed versus what you do if you do that using the theoretical approach for the inverse calculation, okay? Now, the problem, and I will just remind myself of the terms or the terminology which is being used for that from the book, if I can see. It's too small for me to see. There are, okay, let me describe this and then I will get the terminology from the book. When you are performing operations, even when you are solving a set of linear equations, okay? When the set of linear equations becomes very large, the solution using the inverse, even the numeric approach to the inverse operation, becomes prohibitively slow. It takes a very long time in order to get to the solution. And there are one of the famous approaches, there are several famous approaches to solve a set of linear equations without having to do matrix inversion. One of the most famous ones is called the Gauss elimination, right? Have you seen that before? It's very basic, right? You've studied it before, right? So remember that the set of equations AX equals B. Now if we expand a little bit and look at A, so let's, for example, look at a 3 by 3. So A11, A12, A13, A21, A22, A23, A31, A32, A33, and then this multiplied by the x1, x2, x3 is going to be equal to B1, B2, B3, for example, okay? When you use the inverse, you try to take this matrix, get the inverse of the matrix, and then multiply it by the other side with the vector, okay? Okay. Now, the other option is, imagine what you do actually in solving the classical set of linear equations, the one that I showed at the start of the class, right? So if you have this 3x1 plus 2x2 equals 5, and maybe 2x1 plus x2 equals 3, for example, okay? Those two equations in two variables, if you want to solve them, the typical way is you would say, okay, I'm gonna try to get rid of one of the variables by combining the equations together. And then this will give me the solution for the other one immediately, and then I take that solution, substitute it in the other equation, and that's gonna give me the solution for the other one. Similarly, when you look at this setup, you try to look at the operation. How does the operation happen? Okay, if for example I want to like reduce the second equation here to become only on two variables, I have to remove this one. How can I do that without affecting the set of linear equations? I can take the first equation, right, which is represented by this row, multiply that equation, or every single coefficient of that equation, including the b side as well, right, with A21 divided by A11, right? So that I get actually at this point A11, right? Sorry, A21, okay? And then here I will get some value, and here I will get some value. Take that scaled equation, subtract it from the second equation, the first part will disappear, right? Now, the next step is you go to the next equation after doing this operation, and then, you will still use the first equation scaled with respect to A31 and subtract it from that one. Then you also get rid of this one. And then you go to the second equation and you try to use it to eliminate this one. So you make the third equation just single variable, which means that you get the value immediately from that equation, right? And the way to do that again is you take this, again, this is no longer A22. It's A22 after two steps or after one step, right? Which is some combination of A22 and A11, okay? And then you take that one, you scale it such that it becomes equal to A32. You scale the whole equation, subtract it from the last one, and you can actually, in this case, eliminate the third one. So your representation becomes an upper triangular. That's the end of the Gaussian elimination, right? Becomes an upper triangle multiplied by the variables equal to some constants on the other side, which means that the last equation will give you immediately x3 value, you take that and you substitute x3 in the previous one, gives you immediately x2 value. You take that, substitute it in the first one, both x1 and x2, it gives you immediately the value. So there is a forward elimination process and then a backward substitution process, right? As you go forward, you are trying to eliminate as we did here. And as you go backward, you substitute this one. You get the value of this one, substitute it here. And then you get the value of the next one. And then you take those two values, substitute them here. You get the value of the third one and so on, okay? That's called the Gauss elimination. And typically the Gauss elimination, you can represent that by set of operations that are very clear what you need to do. And they are all like single multiplication or single division operations, and the total number of operations that you have to do in order to reach that final solution is much less than doing an inverse of the matrix, okay? Now the issue with this so this is kind of what you can think of as an iterative solution. So you start by solving the third equation to get the third variable, and then you go substitute that in the second one, you get the second variable, and then you go and substitute that in the first one to get the first, and so on, right? Now, again, MATLAB has something called Gauss, and you pass the A and the B matrix, the A matrix and the B vector to that, and it's going to do the calculation immediately and give you the answer for, or the solution for the variables. But the issue is that, again, MATLAB, when it's doing this, it's doing multiplications and divisions, right? And MATLAB itself is just a numeric calculator method, and it has finite accuracy, which means, because again, it uses some digital representation similar to any computer program, and that with a finite number of bits. You cannot represent the number with infinite number of bits, right? And as long as you use finite number of bits, this means that you are doing some approximations to your numbers. So a real number that is pi, for example, is never represented with its true value in MATLAB. It's always truncated at some point, because otherwise you will have infinite digits after the decimal point, and this requires infinite storage, infinite calculation time, infinite everything, right? So you have to stop at some point, and you have certain accuracy. Now this accuracy, when you go through an operation which is iterative, in the sense that calculating one value is being used to calculate the next value, and then it's being used to calculate, you have error accumulation, right? And that error accumulation, in many cases, might give you a completely wrong answer, up to the level that you can have a set of linear equations, right? So that's the one that I was trying to look for the term for it, and I will find it from the book right now. But up to the level that, so now we have the issue of numerical accuracy is finite, right? Which means that if we go through iterative calculation process, you end up with error accumulation. Right? And error accumulation can actually cause, not always, but can cause wrong, not just some extra error, causes completely wrong answer. And one example of that is that in some cases, for example, in some cases, okay, your numeric technique or numeric solver, okay, might think, I remember the word now, might think of a set of linear equations with a set of linear equations, ax equals b, as singular, while it's not. So you just go and test the matrix A, and MATLAB will give you it's singular. while it's not. And then that is called an ill-posed matrix. It's a large matrix with many numeric values, but because of the size of the matrix and the kind of the relation between the values inside the matrix, that in many cases they are close to each other, but they are not exactly the same values. When you go and try to calculate the inverse or test that matrix to see whether it's, because again, for a very large matrix, you cannot just look at it and figure out whether it's singular or not, right? And even doing hand calculations, so you always rely on some numeric technique. And in that case, you just go blindly, ask MATLAB to check if it's singular or not, either by saying calculate the inverse, or there is a command in MATLAB that checks whether a particular matrix is singular or not, right? You say rank, right? And it will give you a rank smaller than the number of rows and columns of that matrix, right? And the reason that this is happening is because, as I mentioned, because of the propagation of errors inside the numeric operation of calculating that. In order to overcome that problem, there are measures, for example, that just, again, this is just an example of things that you face in doing numerical solutions. There are measures that allows you to look at a matrix and figure out that that matrix is what we call ill-posed matrix or not. And how much, if we can say ill-posed, how much illness is inside the matrix, right? And that is by comparing some parameters of the matrix. For example, it tries to do A times A inverse, right? And then figure out whether this is as calculated by MATLAB, it should give you I. But sometimes when you do that, because of the numeric calculations, it will give you some value different than I. It will give you a result of A times A inverse, which is not exactly the unit matrix, the I unit matrix. It becomes like 1 and then 1.1, 0.9 on the diagonal, or even some of the supposed to be zero values, they become slightly different. So that's one way to test if a particular matrix is ill-posed or not, which means that you have to be very careful. If it is ill-posed, you have to be very careful when you're using it in more advanced numeric techniques, right? So again, the whole idea here is to keep in mind that you might be using a very correct algorithm, you might be doing the right thing in this problem, but the numeric values that you are dealing with are more challenging, and you need to be extra careful. You need to play with them a little bit to make them within either the domain of accuracy that you are working on, or another issue that faces also numeric solutions is when you have a small amount of your values that are very large, and then the rest of the values that you are dealing with are very small. Now, working with a system that can, the problem is when you are representing things with finite number of bits, you either can increase the precision, so you can represent very small numbers, but then the largest magnitude that you can reach becomes smaller, or you need to increase the amount of the magnitude that you can represent, and accordingly you lose precision, right? In order to overcome this, for example, sometimes they use the logarithmic approach, so that they bring the small and the large close to each other, right? But of course, when you do that, you have to be very careful. When you apply the logarithmic approach or the logarithmic scale, you have to be very careful how to deal with the operations that you are doing, right? Because logarithmic addition is not the same as addition of the two values and so on. So you have to be very careful how to do that. So just, I wanted to mention this in the vicinity of the linear solutions, which are supposed typically to be something very straightforward. But the challenge really rises when you are dealing with large scale numbers and numbers that are close to each other or very apart from each other. Those are two extremes which you have to be very careful when you are dealing with them, okay? I think I'm going to stop now for people to pray, and then we will come back to continue after the prayer. We'll stay a bit longer after the prayer compared to now, but I just don't want to delay you. And then after the prayer, it's going to be a little bit longer time, so bear with me, sorry, because we started a little bit late. So just to go on with the discussion on the solution of a set of linear equations, we mentioned the Gauss elimination, right? So one numeric technique is the Gauss elimination. And there's another one which is a variation of the Gauss elimination called the Gauss-Jordan. Yeah. So Gauss-Jordan. Yeah, with A. Elimination. So remember, the Gauss elimination is using pivoting. Pivoting is just saying that remember when we took the first row, and then the first element of the first row is your pivot, and that one, you're gonna use it to eliminate all the ones below it, right? And then when you go to the second row, the second element in that becomes your pivot, and then you use it to eliminate everything in the column. To eliminate everything in the second column. And then when you go to the third row, your element in the third column becomes your pivot, and then you use it. That's when you go with the forward elimination process, and then when you are going backward, you just get the value from the last row, substitute in the one above, you get the solution, take both of them, substitute in the one above, you get the solution, and so on. That's the backward substitution, okay? Now, one thing, so pivoting and then plus forward elimination, okay, plus backward substitution. Okay. One thing, again, as part of the issues that you might face in the Gauss elimination is that at if you are not careful how you do the pivoting and the elimination process, you might actually encounter one step where your pivot itself becomes 0, right? And in that case, it doesn't do much. It cannot really do anything in the subsequent rows within the same column, right? And in order to make sure that this does not happen except in a very special case when your matrix is actually singular, use something called partial pivoting. In the partial pivoting, you make sure that your pivot, you actually reorder the rows to make sure that the pivot element is the largest among all the other rows. So for example, so something called partial, just as a note, partial pivot or pivoting, okay? For example, let's say that you have this, so 3, 1, 5, and then you have 4, 2, minus 1, and maybe minus 2, 5, 2, for example, okay? So if you just go with in the regular pivoting, you just use the first row, and your pivot element is gonna be the 3, and then you will use the 3 multiplied by 4 over 3 and then subtract it from the next one, and then multiplied by minus 2 over 3, and then subtract it from the last one, or multiplied by 2 directly and add it to the last one, and so on, right? If you want to avoid the situations where you might encounter 0 pivot, you have to do a row exchange. So you bring this guy up and you bring this guy down, and you use this row and this pivot as your pivot point, right? And now this becomes more important when you have really many rows and many columns. Now you have to pick the first one. You have to bring up the one that has the largest pivot value for your pivoting column at that stage, okay? That's called partial. They call that, I don't know why they call it partial. They call it partial pivoting, okay? Which is basically trying to always capitalize on the maximum. And then the criteria of this is that you will find that you will not encounter 0 pivots except in the case where you actually have linearly dependent columns or rows. And in that case, your matrix is actually singular in the first place, okay? This is for the Gauss elimination. Now, a variation of the Gauss elimination is the Gauss-Jordan elimination. And in that one, rather than trying to reach, so in this one, we were trying to reach an upper triangular matrix, right? That's the final objective that you need to achieve from the Gauss elimination. From the Gauss-Jordan elimination, you are trying to reach an identity matrix. So you play with the columns also, not only the rows. So you start exchanging columns. You have to be careful that when you are exchanging columns, you are dealing with different variables. So it's as if you are reordering the variables, okay? So you have to be careful about that, and you have to take care of that if you are writing a program using the Gauss-Jordan by yourself. But the important thing is, once you reach, imagine that you started with the A matrix, and then you have the X's, and then you have the B, right? If you make this become an I, which means that you have 1, 1, 1, zeros everywhere else, right? This means that you are no longer, you don't need to substitute. Every single row will give you immediate value of one of the variables, right? Again, the idea of doing this is very similar to the Gauss elimination. So you try to subtract, but you also try to, the remaining variable, you try to normalize that to 1. And in order to be able to reach that in all columns and rows such that you end up with 1 only on the diagonal, the only way to do that is not only by doing elimination between the rows and reordering between the rows, which is the partial pivoting. You have to also do some reordering between the columns. You don't, of course, do elimination between the columns because it doesn't mean anything, but sometimes you have to reorder the columns such that you make sure you bring the zeros to the upper and the lower part and you only have ones in the diagonal, okay? Keeping in mind that when you reorder columns, you are actually doing change of arrangement of variables. So x1 becomes x2, for example, and x2 becomes x1, and so on, okay? So you have to keep that in mind. The operation where you reorder the columns is going to switch the order of the variables as well, okay? Now, one thing that you have to keep in mind also is that all these operations where you are reordering rows or reordering columns are called permutation operations, right? And they can be represented by multiplication by a unity, a matrix with all the elements 0, except the ones that you want to change their order are given by 1. And I'll give you just one example of that, right? Imagine, for example, that you have this matrix, 3, 1, 5, 2, 5, 7, whatever value, 6, minus 1, minus 2, for example. That's your A matrix, okay? And look what happens when you multiply this matrix. Of course, if you multiply this matrix by a unity matrix, the output is going to be the exact same matrix, right? Now look what happened if you multiply this matrix by a reordered unity. So for example, we have this, and we have this. Now notice that this is the last row of the unity, right? But this is supposed to be the first row of the unity, and this is supposed to be the second. So in this one, this is an identity or a unity, you call it identity. This is an identity matrix, but you have switched the first and the second row in place of each other, right? Now notice what will happen. What's going to be the result of this? Okay. So if you multiply this by the matrix A, what you will get on the other side is going to be the following. So 0, so you'll have the 2 here, right? 0, sorry. 0, yes, 0, the first row, so you'll have the 2, and then you multiply this by the second, you have the 5, and then you multiply it by the third, you have the 7, right? That's the first row multiplied by all the columns of the other. And then the second one, you will have the 3, and then you will have the 1, and then you will have the 5, and then the last one, you will have exactly the same thing, 6 minus 1 minus 1. So by multiplying the matrix A with a permuted identity matrix, where you changed the rows one in place of the other, the result was when you go manually and take the second row of the matrix A, put it as first and take, so reordering of rows can be represented by a matrix multiplication operation. Similarly, reordering of columns can be represented by a matrix multiplication operation, okay? So this tells you that even those operations, it's not really that the program that you write is going to go and like take this and put it in a different memory place and so on. It's just simply multiplying the matrix by some shuffled identity matrix, and that will give you the effect of permuting the rows or permuting the columns. We call those exchange of rows and columns permutation operation, okay? And you can see, if I want to do a sequence of those, it's simply multiplying by as many matrices to the left as you want. And this is gonna be applied first, and then this, and then this, and so on, right? Okay? So you can always represent that by matrix multiplication operation. Now, why did I mention this? I mentioned this, number one, because of the Gauss-Jordan. So basically, when you want to exchange columns or you want to exchange rows, these can be represented by matrix multiplications. That's number one. And number two, that this happens a lot in something called factorization. And that's the last topic I think we'll talk about today. Yeah. So factorization is a way of representing. So let me make, yes, okay. Factorization. Matrix, of course, we're talking about matrix factorization, not prime number factorization, okay? So matrix factorization. You have a matrix A, and you want to represent that as a multiplication of two matrices that have desired properties. For example, you can represent A as an upper triangular multiplied by a lower triangular matrix. Call the first one U and the second one L, right? Or you can represent the matrix A with something called the singular value decomposition or the singular value factorization. So you can represent that by the SVD representation. You can represent that by an upper triangular multiplied by lambda. This is the eigenvalue factorization. Singular value is, where is that? I need my reading glasses. Yeah. Yes. X equals B. This is upper and lower. Singular value decomposition. Yes. So you have an upper. So for the singular value decomposition, you have an upper and Q. No, this is the Q factorization. Where is that? Yeah. Singular. Yes. So you have an upper. Yeah. You have an upper triangular matrix, and then an S matrix and a V Hermitian matrix, okay, or vector matrix, sorry, okay. And the upper triangular matrix is well known, so it just has zeros on everything below the diagonal, and then the V is the vector of or the matrix of eigenvectors. Remember that you can represent. You know what's the eigenvector representation, right? Or eigenvalue, eigenvector analysis, right? You know it? Okay. Remember that any matrix A, if it fits all the properties of not being singular and all these, like not L-posed, so a matrix which is in good condition, can be represented by something called the eigenvalue decomposition of that matrix. And the whole idea of the eigenvalue is you have this equation, right? A multiplied by sorry حد قال حاجة؟ No? Okay. So in the eigenvalue decomposition you have A multiplied by lambda I minus V, right? Equals 0, right? So you can find a set of parameters, lambdas, that called the eigenvalues, and corresponding to each one of them something called an eigenvector, right? And then the result of multiplying lambda I minus V with the matrix A is equal to 0, right? Am I correct?
What does lambda?
Sorry? It's represented as
Lambda I minus A equals
lambda, sorry? It's represented as A minus lambda A, right? Equals 0. Sorry, equals AV minus lambda A equals 0, right? This is the representation. So it becomes no. A minus lambda, it's this on this side and it's equal V on the other side. Yes. So it becomes A multiplied by I AV minus lambda equals 0. I think this is the correct expression. So A multiplied by lambda I the other way. Lambda A minus A V. A, sorry?
A minus lambda I equals 0.
لا where is the I, where are the eigenvectors? A minus lambda I?
this one is
No. I think it's A lambda A minus AV equals 0, right? And then the result of that is gonna be that A multiplied by lambda times I minus V is equal to 0. Yes, if I remember correctly. And then the whole idea here is those lambdas, they represent a certain property of the matrix, right? They call them the eigenvalues of the matrix. Again, here they just represent that a particular vector. The idea here is that a particular vector, when multiplied, which is called the eigenvector, when multiplied by this matrix A, results in this is simple scaling, right? So here you multiply by a vector, here you end up with just a scaling value. The matrix stays as it is, and you only scale it by a scalar value, right? So this is nice because this vector, typically what happens when you multiply a matrix by a vector, you end up with rotation. But here, those eigenvalues and eigenvectors, they give you a scaling without any rotation. Okay? That's the idea of the eigenvalues and the eigenvectors. Again, I might have written the formula incorrectly. I will get it to you correctly. I did not refresh my formulas of linear algebra. But anyways, the SVD decomposition is representing the matrix in this formula, and the V is the U is the, okay. Yeah, so the SVD decomposition is, okay. So it says that these two are unitary matrices. Unitary is an orthogonal unitary matrix. So this is a unitary, and this is also a unitary matrix. And they are orthogonal to each other, so the U and the V are orthogonal to each other. And the S is a diagonal matrix, and this is a diagonal one. Okay, that's the singular value decomposition. What's the benefit of unitary matrix? I don't know, but of course diagonal matrices are Diagonal matrices are matrices that has only values on the diagonal and they don't have anything above or below. So typically those for calculations, for certain calculations, they become very easy. If I remember correctly, this particular decomposition can be used to deduce the inverse of the matrix by simply doing some operations on a diagonal matrix only. So I don't remember the formula, but there is a formula that maps the inversion of a matrix to performing operations on the diagonal of the singular value decomposition. So if you can represent the matrix using the singular value decomposition, and then you want to invert that, you just go to that diagonal matrix and you perform some operations on it, and that's it. You don't need to perform all the other complicated operations that you need to do in regular inversion. Okay. The other one is the upper-lower triangular, as we mentioned, the UL. That's another factorization. Why did we go into factorization? So what I wanted to mention is when you are doing factorization of a matrix, representing it in a desired way, in a multiplication of desired matrices, you do a lot of permutation operations. And as I mentioned a couple of minutes ago, those permutation operations are simple multiplications by an identity matrix with rows or columns permuted in each other's place. Okay, I think this is more or less what I wanted to. Yeah, there is the remaining part is about iterative methods to solve equations. I'm not gonna go into. You know what? We can mention that it's not really okay. In many cases, we are still dealing with linear situations here. Okay, in many cases, you can actually do solution of coupled equations or simultaneous equations by starting at a certain point, right? Substitute a set of values for the variables, and then move in a kind of a clever way from one substitution to the other. So basically, you have the set of equations, right? Represented by ax equals b. So we just write the equations themselves. So you have a 11x1 plus a12x2 plus up to an xn, a1n xn, a21 up to a 2n xn, and then we go, in the general case, you go up to a m1 x1 plus, right, up to a mn xn, and then each one of those is minus b1 minus b2 up to minus bm, right? Okay, and all of these are equal to 0. Okay. Now, one approach also to solving simultaneous equations is that you start, which is called the iterative approach. You start with just, let's say, in the general sense, randomly allocated values for x1, x2, x3, and so on. Okay, so you just put values, and then you calculate this equation. You will find that the equation is not giving you 0, of course, right? Unless by luck you figure the values from the first time, right? And you do the same for the rest of the equations. Okay, I'm not going to describe the exact algorithm. I'm going to describe the concept in general. Okay, and based on how much you are deviated from the set of zeros that you should achieve here, you will get an error vector. Right? It's rather than zeros, you will get some values for each one of those equations, which represents some kind of an error vector. That error vector can give you a direction whether you should increase or decrease the different values of the x's, okay, by doing some operations on that error vector that you get. It will give you an intuition whether you need to increase, for example, the value of x1 from the initial that you started with, decrease the value of x2, and so on, right? Now, the idea of increasing the values or decreasing them is dependent on what we call the convergence. the convergence of an iterative algorithm or of a numeric algorithm is the guarantee that from one step to the next step, you are moving closer to the solution. Okay? If from one step to another step, you don't know whether you are getting closer or further from the solution, then this algorithm is not functioning because you don't know where you will end, right? But if from one step to the next step, you are always getting closer to the solution, even with very small value, then this means that you are converging to that value. Okay. Typically, to calculate the convergence, as I mentioned here, you calculate the error, right? Represent the error somehow in terms of the number of steps in relation to the previous step, right? And then you show that using this particular algorithm, I can guarantee that the error is always going to become smaller with the operation that I am performing through one cycle of the iteration. So through one iteration, the error becomes smaller, which means that I'm converging or becoming closer to the actual solution. There are a few methods for solving linear equations that uses this approach. One of them is called the Gauss-Seidel iteration. And which is the other one? There is another one as well in the book. Jacob. Yeah. Where is it? It has the word Jacob, but where is it? Whether you remember the name, say it. Jacobi iteration. Yes, Jacob, yeah. Jacob, yeah. Jacobi, yes. Jacobi iteration and the Gauss-Seidel iteration. Okay, and in most of those, you don't really start with all the variables allocated. Okay, you start with reduced equations, and you like what you get in the from the Gauss elimination, for example, and then you substitute the values in that one, and you start moving to higher order equations to get the value. I'm going to describe those in more details next time, in terms of describing how the algorithm works. You can have a look at it until we come to next time. It has a nice diagram at the end that talks about the convergence. We'll also discuss that. So next time, I'm going to start with this, the iterative approaches for linear. And the next topic that I will move to is not going to be, I think the next chapter in the book is about nonlinear equation. The nonlinear equations, right? I skip interpolation. The next one, the one after that is nonlinear equations, right? The third, this is second. The third is interpolation. The fourth is nonlinear equations. I'm going to touch on the nonlinear equations very roughly because, again, in the undergrad courses, they are typically addressed, whether you talk about Newton-Raphson or what's the other? There's also another one with Gauss and Newton, something like that. So those ones, I'm gonna just go quickly over them, and I will move directly to ordinary differential equations. I think this is more where we need to be at the level of this course, okay? There will be an assignment.